All right, welcome back again to HYSYS Academy. All right, so today we are going to be looking at dynamic control. We're going to continue from where we stopped, and then we are looking at module 4.1, understanding the PID controller. All right, so let's move on. What is the PID controller? All right, so the PID controller stands for, the PID actually stands for proportional, integral, and derivative. Now, these three control actions combine to form one of the most widely used control strategies in process system. All right, so basically each of these, that's the proportional, we have the proportional controller, we have the integral controller, and then we have the derivative controller. Now, when you combine these three together, separately they are controllers on their own, but when you combine them together, that's when you have the full PID controller, giving you just one control at the end of the day when you put the three of them together. Alright, that's basically what the PID controller is for, and that is what it means. This is what it stands for. Okay, so let's quickly do a breakdown of this PID components. Alright, so the first component we have is the proportional controller, right? This helps the system move quickly towards a set point. Now you'll be having a set point in your, that's like a target you're trying to achieve. A set point, you don't want it to exceed that particular point. It shouldn't go below or it shouldn't go above that point. That's your set point, and that's what you're trying to achieve. All right, so um when you do that, yeah, it's your, you're trying to make sure that, okay, the proportional controller helps you to move towards that set point. All right, very soon I'll be drawing some graphs for you to understand how it works. Okay, so it helps you to move towards that set point. All right, then it controls the speed of response. All right, so it controls how this the variable move towards a set point. All right, it controls how it moves towards a set point. It controls the speed it goes to that set point. So it might be slow, it might be fast. It controls the speed of response depending on what you give to it. All right, and then usually it is represented by kp or kc. All right, this is for the gain. The gain is represented by kp or kc. That's like a constant, and then it acts based on current errors. All right, so it works based on the current error at that time of the system. As the system is running, it runs based on that current error. I'll be explaining that. Let's see what the integral controller is all about. Now, the integral controller works to eliminate steady state error by integrating past error. So now it looks at the past error, just like what we had in the proportional. The proportional will use it uses the current error. Now, from the errors of the proportional controller, it now integrates it in such a way that it improves the accuracy over time. All right, it gets the error, maybe it's like maybe +5 or -5, depending on how it is above the set point, whether it's an overshoot or it is an undershoot, depending on how it is. Okay, so it gets this error and then now it improves it to get the accuracy over time. Right, it helps the system to get more accurate. It increases the accuracy over time. Okay, so basically you can say that the pi, that's the proportional controller, it takes you to where you want to go to. It takes you to the set point. Now the integral controller actually helps you to it increases the speed. All right, it makes it faster. It makes system works faster to get to that set point you're looking for. I will be explaining this in a graph shortly. All right, so it is represented by ki and typically modeled as ki stroke r, depending, but most times you see it as ki. You see, all right. Okay, so um it acts based on accumulated error, that's history. It acts based on history, just like the first one. We said it eliminates the steady state error. It looks at the steady state error by integrating past error. Looks at the steady state error. Now remember, you're going to the dynamic mode. It gets the error from there, and also from the error from your pi controller, and then it works on it. Sorry, your p controller, that's a proportional controller, works on it, and then it gives you a more accurate result over time. All right, so um let's move on to the derivative. Now, what does the derivative do? All right, so it predicts the system behavior and damps oscillation. All right, so it observes your integral controller, and then it helps you to improve your accuracy. Like it helps you to settle more at the set point. All right, like I say, it helps to reduce overshoot and settling time. Okay, so it observes your integral controller, because the integral controller will want you to get your settling point faster. All right, it helps you to want to get your settling point faster. Now the derivatives helps you to get to that point. It reduces the overshoot, it dampens the oscillation, so it doesn't have to keep oscillating continuously, but it helps it to get to the steady point, to the steady state over time. All right, so it helps to reduce overshoot and settling time. All right, and then usually represented by KD, and it acts based on rate of change of error, usually like a future trend. All right, so it helps to observe the future trend, and then it helps to adjust it so that it will remain at that set point. Okay, so now let me quickly explain what all this is trying to say. Okay, so let me bring this. Let me draw some. Let's draw a graph. Let's draw a graph. Very big graph. Okay, let me try and move this so that's it. Okay, sucks. That shapes. Okay, let's quickly change to black so I can see better. Alright, so I move this to this point. Okay. Alright, so let's say the straight line. Let's say my set point is right here. This is my set point. This is my set point. Change to black. Okay. It's not straight. Okay, this is my set point. Usually this is time, and then this is usually what you have here is time, and then you can have any variable you're trying to use here. So let me quickly insert like a text. Okay, let's see, this is time. Say this is pressure. Pressure here. Let's see, pressure at this point here is, let's give this 50 kPa. 50 kPa. All right. Okay, all right, so the set point is 50 kPa. Now what we have, let's insert this case of the curve. All right, so when it starts, when you've put in your controller, setting your inputs, your intervals and everything, and then you've tuned your controller now the first thing it does, remember, the first thing it does is it takes the variable to the set point. Now 50 is the set point, 50 kPa is the set point. All right, so I decide to move from here. I'm moving from here, get to this point. Most times it overshoots. All right, when it's past the set point, that's your overshoot. Okay, I don't like this. It's 22 straight. Let's do this again. Let's do that again. So select our curve. Here we go again. Go. It's moving and then it overshoots. Once it overshoots, we have to allow it to oscillate a little bit. Now this is called oscillation. Now it goes below. That's how it tends to be. Now from the start point to it gets to the set point. Now that's the job of your P controller, that's the job of the proportional controller, right? So once it begins to overshoot and then comes down below, now we have to go back again, tries to go back to get to the set point. Now this thing that is happening here is called oscillation, right? So now your integral controller kicks in, and then remember we're trying to get to, it reduces the overshoot and then the error. So now instead of it coming back to this point, your integral controller kicks in, it reduces the oscillation. Now it's going to be coming down, right? And then not good this. I'll just move from here. Okay. So at this point to your derivative too, we tend to kick in, and then because the thing is trying to achieve this faster, so it makes it to move closer. All right, moves closer, moves closer, moves closer. Reduces the oscillation, reduces the oscillation, and then going with you have. I still be moving a little bit, but okay. So yes. All right, so let me explain this again. So usually from this point going up, that's your proportional controller doing the work here. It overshoots. Now when it passes the point, it overshoots. If you are trying to see undershoot, it won't reach this point. Just from here go back down, right? And then it goes back up again. All right, then it comes down. Now your PI control, your either your eye controller or integral controller, like I said, it improves the accuracy over time. It works to eliminate the errors. Now so it's eliminating this error, it's reducing the error which we used to pass the set point. It reduces the error, and then like I said, it's improves the accuracy. All right, so now it's coming closer to our set point line, and then we see it reduces the error, keeps reducing the error. All right, so and then for our derivative, it helps to predict the behavior and dampen the oscillation. So dampens the oscillation. By the time it observes that okay, it's trying to see, it also helps to reduce the overshoot and settling time. So it makes this to settle faster. Maybe this was supposed to happen over like 50 different oscillations. It reduces it, and then like I say, it dampens the oscillation, makes it smaller, and then defining it, it gets to the steady state, which is the set point we are looking at, and then it keeps going down. So basically that's how the controller tends to work. All right, that's basically how it tends to work. Okay, so moving further, let's reduce this. All right, so how does the gain work? So like we say, kp is the proportional gain for, that's proportional gain. It reacts to prevent error. All right, the ki is integral gain, reacts to accumulate, reacts to the accumulation. Okay, it reacts to the present error, like we said before. The ki reacts to the accumulation of past error from the error from the kp. All right, and then the kd, that's the derivative gain. It reacts to predict the future error. I've stated this before. Now working with this, balancing everything together gives us fast response, reduce error, and stability. Now everything working together gives us our PID controller itself. All right, so now we have some rules that we follow when we are trying to use our PID controller. All right, so the first one we have the P, which is it used to look at we have the fast system. That's like you are trying to do like a flow control, like a fast system, and then we have the slow system. So looking at the fast system, when you're using your P, all right, you lower your K, that's the gain, you lower the KP, you lower the gain, all right, because a high gain can cause cyclic or oscillatory behavior. All right, so when you are working with a very fast system, you reduce your P, that's the value you'll be giving to your KP. All right, so that's what you'll be doing. Okay, to reduce that oscillation behavior. All right, so you increase the ki to eliminate the errors quickly. So you increase the ki so that the error can be eliminated quickly. Remember, the system is very fast. It will overshoot, come back, um, go below the set point, go above it, come below it. It's going to be so fast. So in that point, you reduce the kp, you increase the ki, all right, to eliminate the errors quickly. And then sometimes you might not often need the the KD for the fast responses. All right, and then now when you're coming to the slow response, you have to let's go back. So coming down, all right, so coming down to the all right, so coming down to the slow system, you use a higher KP. All right, so to increase the response to be quicker. Remember, the first one, since it's too fast, we have to reduce it. Now that it's slow, we need to increase the response, and then we have to now reduce our kp. Kp will be smaller as a smaller ki. Sorry, ki will be smaller. All right, so ki will be smaller to avoid excessive overshoot there, and then the kd is going to be smaller. Most times kd and ki tend to work in the same proportion, all right, because they have similar uses. Most times, if you can't work with when you have like a constant zero, most times it won't work that way. So basically, most times your kd and ki, they tend to work alike. All right, so your kd is smaller than your ki. All right, it has to be smaller than the ki to improve the stability, but at the same time, it's still small. All right, in terms of proportion, it's still small. All right, the ki is smaller than the kp, and then the kp has to be increased higher. All right, so that's how you go about your PID controller. That's how the PID controller tends to work. All right, so we have a quick example that we can follow. We have a quick example to follow so that we can see how to set up this PID controller. All right, so we have the system. We have a feed enters at a pressure of 20 psi with a temperature of 80 Celsius. Mass flow rate is 5 kilogram per second. All right, this is the feed composition. It's a mass fraction. We have acetone, we have 2 propanol and water, and then we have the operating pressure of the drum, which is a flash drum, is 14.7 psi, and the pressure of liquid and vapor at downstream is 9.7. All right, so this is what we are trying to replicate in our Aspen HYSYS system. This is the flow diagram which we're going to be replicating. All right, so let's go now. Let's get to our Aspen HYSYS. All right, so remember the first thing, your components, very, very important. We have acetone. All right, we have 2 propanol, and then we have water. Okay, so having done that, we go to our fluid package. We are going to be making use of the Uniqua, sorry. All right, so it's compatible, it's okay, we move on. Going to the simulation environment, how I feel I have explained to you also why we make use of when we tend to make use of the uniqua and when we tend to make use of other thermodynamic properties. Alright, so let's go further. If you haven't checked our second, that's module 2, go over module 2 again, and then you see we tend to use certain parameters or certain thermodynamic properties for different compositions. Alright, so this first one is our feed. Name it as feed. Okay, temperature is given as 80. Pressure is given as, let's open this. Pressure is given as 20 psi with 5 kilogram per second. Alright, so 20 psi, mass flow 5 kilogram per second. Alright, composition, remember it's mass fraction. Okay, close this. Now for acetone. Let's get to acetone. Acetone is given as 0.294. So let's impute 0.294. 0.294. All right. The propanol is given as 0.484. 0.484, and then the last one, which is water, is given as 0.222. All right, so everything is equal to 1. Yep, our system is running properly. We have a valve, control valve comes in. Okay, this is our feed. All right, see our product is let's say V1 out. V1 out on delta P. Continue. We have a separator. It's going into a separator based on the diagram we have. All right, so open it. V1 out. We have VAP. Let's put VAP. Let's put LIQ caps. That's liquid. All right, and at this point we have another valve. I think we have one more down here. Let's see our diagram so we know we are following it properly. Okay, flash drum, feed valve, vapor coming out, liquid valve, liquid coming out. All right, so let's continue. Okay, change the name of this to flash drum. All right, we have the flash drum. Okay, all right, let's continue. Okay, that is going in, and then we call this vapor. Okay, and then the liquid is coming, and we call the outlets liquid. All right. Let's get some multiple. So let's check the specifications. We have this, so we can complete. All right, so it said the operating pressure of the drum is 14.7 psia. So to do that, we come to the drum, open it, check under dynamic, as the vessel pressure. We have to remember we're going to the dynamic state, and then we impute our, what's this, 14.7. So we put in 14.7 kPa. Okay, y 10.7 psi, sorry. Okay, right, so it refused to work from here, and now way to do it is to come directly to our inlet, which is the V1 out, and then we just put in the vapor here. That's 14.7 ps. Right, okay, so after doing that, we have, I said, the operating and the pressure of the liquid and vapor at the downstream is 9.7. All right, so we have to specify the vapor and the liquid as 9.7 psi. So we come down here, select my vapor, put in my 9.7 psi. So, okay, that's solved. And then I did the same thing for this guy. That's for the liquid, 9.7 psi. All right, so after doing that, now we need to, okay, so after doing that, now we need to add in our control system. That's the PID. You can see under dynamic and control, you see your PID. We'll just make use of 2 for now, and then come here. Okay, let me remove this. Let me show you something different. Right, I'm adding this for, and then I'm adding this for the liquid. Sorry, I wasn't supposed to do this. All right, so let's start with the feed. The question continues. We have a feed. All right, so the feed FC, that's your controller. That's the first controller for the feed control. All right, so let's open that. It's this particular controller here is going to be controlling the feed, and then it's going to be the valve as well. So it's going to be like a feedback controller, because the feed from here will determine the opening of the valve, how it's going to be opening. So this is very what is going into our flash drum. All right, so that's basically what we're trying to do. And then we select our variable source. We select all right, we select v v100, sorry, v out, v1 out, v1 out. We select mass flow, right, and then the output is the VLV actuator desired position. All right, so he's talking about unknown ranges. So I'll change this. See, it says this, let me quickly flip this so I don't get confused. Okay, it's fine this way. All right, so it's in unknown range. All right, so let's put in, see our KC. Now the TI is for the integral, and then the TD is for the derivative. All right, so from what we have in the question, we have 5.29 as the KC. So we put 5.29 as the KC. All right, then we have TI. Now mind you, this, what we are getting now, has been calculated. In the subsequent video, I'll be showing you how to do the calculation, how to get your KC, your TI, and then the TD. All right, okay, so our TI is 0.06 0.660. So let's quickly get back to that. 0.660, 0.660, and then the TD which we are going to be using is 1.05e minus 2. All right, 0.05 e raised to the power minus 2. Okay. All right, so now this is okay. Minimum, maximum. Let's say we don't want it to exceed. The price was like 5 kPa, 5 kilograms, kilogram per second. So let's see. Then another thing we need to do is to make sure that this is on manual. First put it on manual. Let's move it to auto. Okay. I think because of that. Alright, so let's say we don't want it to go below. Minimum is 0. 0, and then the maximum we don't want it to be above, no matter the feed shouldn't exceed, let's say 10. Let's say 10. This is actually too high, 10 kilogram per second. All right, this is it, 10 kilogram per second. Now it's a manual. Okay, so the set point is at 5. Automatically sets the set point at 5 for us. That's after taking the range. If I change it to, right, because our SIN is in kilogram per second, so we leave it that way. So kilogram per hour. All right, so moving forward, let's go. Let's close this. All right, so our feed controller is ready. Now we need to do the level controller for this. All right, so I come into the dynamic state. Okay, what we're trying to impute has done it for us. I need to configure the level controller for this so that it doesn't exceed a particular stage. So we'll be putting in my level controller, so it automatically selected the level percent for us, and then it went down to the VLV2. All right, so it's trying to control the liquid in this flash drum for us. All right, so coming to the parameters, this is the parameter it gave us initially. All right, this is what it's working with, this is what it feels we should work with. All right, but we can also change it to what we want. All right, so when we want to change it to what we want now, remember this is going to be when it comes to flow. Remember we gave two examples when we have the slow and then the fast. Let's see that again. All right, so for the fast system and the slow system, now remember this is a fast system because of we're trying to control the level of flow. Remember it's a flow. The trying to control the level of flow in here. Liquid is coming out, so you know how liquid tends to move, and then it's going to be a fast process. So basically we're not going to be having our TD. All right, remember from the example we gave, we're not having the TD. We can just work with the KI and then the KC. All right, so let's put in the values for what we have. All right, let's come down to here. Okay, so we have the KC at 0.5 and then the time is 5 minutes. All right, KC 0.5, the response time now is 0 for the KC 0.5, and then it's 5 minutes. All right, we're not having this. Everything seems to be okay. Minimum, maximum 100%. Our set point, we want it to be at 50%. All right, so keep it on auto. Still going to move this one to auto too. All right, so it asked for CV. There's a CV value given here. All right, it asks for CV, giving it as a 55. Now where we are going to be working with that is with our VLV. All right, so we come to ratings. We see our CV here. All right, so the valve opening is 50%. It's fine. We change this to 55. All right, and then we allow system to do its thing. Okay, so now we have to go to the dynamic mode. Now going into the dynamic mode, we click on dynamic. All right, yes, allow it to make changes. We don't have the volume, we allow it to calculate the volume for you based on the specifications. So we say make changes and then finish. All right, so the integrator, now we have the current time, which is 0. We have the accelerator and then the end time. Let's say we want this to end in 60 minutes. Okay, and then we want the acceleration to be like 0.1 so that it won't be too fast, starting from 0. 0 is the start point. All right, you can leave this as it is. All right, so this is fine. All right, this is fine. Then another thing we need to generate is our strip chart. Now remember, we're trying to control the level of liquid in this flash drum at the moment, so we have to bring in our strip charts. You can add your strip chart from different ways. I can add my strip chart from here. Just come to create this, come to strip charts. I can select this and then create strip chart first. All right, and then I can just say display. Now you have a graph. Now you can use it to monitor your the controller here. Look at that. But remember, our main focus is to see the level controller here, how it's working. So I come to my strip chart, I add a new one. All right, add a new one. I click on add. So we are looking at the flash drum. We're looking at the volume percent. Liquid volume percent. We add this. Done. We add another variable, which is from the level controller. That's this. Say the set point, which is SP. All right, this is the set point SP, and then we add it to it and click on done. Once you're done with this, you click on display. This will come up. Now you can monitor how the level of the flash drum, and then see how the controller helps to regulate the flow of the liquid in it. All right, so remember, this one is for the FI, that's the feed controller. All right, so after doing this, you click on the dynamic state again. You say, are you sure? You click yes. All right, so I just click on run. I've set my integrator for 60 minutes and then I allow it to run. Okay, allow it to run. Remember, this is what we're trying to monitor. Open this. All right, so it's telling us that I think this is done already. This is done. So initially it's dropped because the initial condition was set to 50. That's from our separate the tank itself. So I think we need to reduce 30 from 0, but you can see that it wasn't. Now this right here is, well, since it wasn't able to get to our 50 set point, that's what we call the undershoot. All right, it hasn't gotten to that point yet. All right, so maybe I can increase my time. Let's say we do this for the next, say 120, let's say 183 hours. Let's reset this. Yes, reset. Okay, and then we run it again from the beginning. Right, so you can see it's gradually trying to climb. It's gradually trying to climb. It's gradually trying to climb to that point. It's going higher. It's going higher. It's going higher. It's going higher. Alright, so it ended at 15. Alright, so let's tweak something here. Let's tweak something in here. Okay. Let's see what happens. Let's see what happens by the time we make this to run a bit faster. Okay, there are my graphs. Alright, let's reset this. Now I can see that I want this thing to be in my real time. If I'm running on real time, I have to actually wait for 3 hours, but I'm not doing that. Alright, so let's run it. Recording operation. Alright, so it didn't work. Failed to initialize. Let me quickly check this. Valve opening. Alright, this is okay. Alright, let me check my flash drum. Let's make it the initial conditions to be at 0. Alright, make it to be at 0, and then let's allow it to set this. Too many specifications. Make changes, yes. Finish. Close this. Let's go to dynamic. Alright, this time to run again. It's running now. Are we going to get there this time? Okay, now it's even less. Alright, now it's even less. Okay, so set integrator. Let's come back here. Let's put this at 0. What did we have before? Let's take it back to the normal condition, which is 0.5. Alright, 0.5. Okay, so I think we need to, let's check. We've not really checked our HYSYS. Let's see what the HYSYS is saying. That's the feed controller. Alright, so let's auto scale all axes. I think we have to run this again. Okay. So the HYSYS is just, this is the level, it's just a little bit above. It is 5 kg/h. This is the PV, that's 4.9. Alright, so it is done. So basically we can, I think, let's to scale this. Scale curve starting from alright, so this is that it achieves steady state at the point. I can easily check my alright. Okay, this now is at 23. We close is 23. Okay, we actually want it to get to 50. Basically want it to get to 50. I feel if you increase the time actually to get there eventually, let's say times 2, that's 6 hours. Let's see. I'm going to reset everything. Let's do this for 6 hours. I think it's 6 hours we should get what we're looking for. Alright, let's go. Alright. Okay, we're getting there. Very close. Okay. I think we're about to experience a little bit of overshoots if we put some. Okay, didn't get there. That's based on the conditions we're having. Let me get this since it wants to be funny. Let's do 10 hours. Let's observe it in 10 hours. Okay, reset actually. Let's set another time to this. Okay, it's doing it for another 10 hours. So let's stop this. I think we've achieved what we're trying to get from here. Let's alright, so you can see that based on what we have, it went to the 50%, and then you can see that it stayed at that point. It stayed there, it just remained there. It didn't overshoot, and then it didn't overshoot. At the same time, it didn't undershoot. Once it got to 50, it tried to remain at that point. Alright, so if we didn't have the controller system there, it could have gone above the 50, and then it won't it won't keep it at 50. So likewise, if I decide to change my set point to be at it has to be at 70%. Alright, I want it to be at 70%. I reset this and then allow it to run 70%. Let me auto scale this. Alright, you can see that now it's at 70. Okay, now the new set point is 70, and then this is trying to meet up with that. It's actually very good. Let me stop this. Okay, let's check my valve conditions. So I want this to be from 0, and then let's see. Let's initialize y. So changes, make the changes, finish, activate. Let's go back to dynamic state. To scale. Okay, this is at 70. This is less. Consider it's changing, but it's changing very, very small. It's making minor changes. It's making minor changes. Alright, so basically that's how you go about your controllers. You can decide to tune it, to change it. Remember, what really matters is your KC, KI, and the rest. Alright, so this is how you set up your controller. With time, I'll be teaching you how to calculate all this: the KC, the KI, the KD. You have different methods for it, right? So basically, this is how you set up your PID controller. You set what do you want the system to control. You are controlling the feed rate by regulating the opening of this valve, and then at this point you are controlling the level of this drum by regulating the flow out of this point here. All right, so basically that is how you go about your control system. All right, so with that, we call it today. See you in the next class. We'll be looking at the uh, cascade controller. All right, thank you very much.